Hi, everyone. I'm Sandy Lucas. I'm the program manager for NOAA's Climate Variability and Predictability Program. Thank you for joining us for this webinar series called Years of Maritime Continent and Piston Field Campaign. This is a continuation of a series of webinars for the CVP program that started several years ago. Today's webinars are being recorded and will be available from the CPO website under the Climate Variability and Predictability section. If you've missed any of our prior talks in the past CVP webinars, such as the first two talks in this series that was presented by Chidong Zhang and Jim Mohm, I encourage you to view them from our website. Those sessions are posted now. I'd like to start today with a bit of background on the importance of these YMC and piston projects. The Years of Maritime Continent is an ongoing set of international field campaigns and modeling efforts focused on the Maritime Continent region. YMC is led by the countries of Japan, Indonesia, and the US, in partnership with many others, such as Malaysia, Australia, the United Kingdom, the Philippines, and China. Of particular interest to NOAA and the CVP program is to improve understanding of processes that affect the propagation of intraseasonal oscillations, such as MJO, in the Maritime Continent region and its broader regions. MJO is important to local weather and climate, as well as having global teleconnections. However, the Maritime Continent can sometimes act as a barrier to the propagation of MJO, and weather and climate models have a hard time reproducing this effect. In response to that need, the Climate Variability and Predictability Program solicited observation and modeling projects that investigate different processes that affect the speed, intensity, disruption, and/or geographic placement of the MJO propagation in the Maritime Continent region. Additionally, in collaboration with the Office of Naval Research, CVP supported several activities of the Piston Campaign. This year's webinar series covers the 16 projects funded by CVP. I really look forward to hearing the results of this webinar series. I would like to thank Gabriela Jeliazkov, the CVP student visitor and the organizer of this series, for all of the hard work that she has done putting this together. At this point, I'm going to turn it over to Gabriela for the full introduction of this series and the introduction of the speakers today. So whenever you're ready, Gabriela, please go ahead.
Great, thank you so much, Sandy. Hello, everybody, and welcome to the second of 10 webinar sessions on the topic of Years of Maritime Continent, which will feature 2 presentations per session and will run from September 10th, 2020 to March 11th, 2021. This series of presentations will share the latest results from these projects and will allow the PIs to discuss the importance of their work, outcomes, and lessons learned today with the broader scientific community. We hope you will enjoy today's talks and ask plenty of questions. As you listen to the presentations, if you have a question you would like to ask the presenter, please raise your hand. Raise your hand is a feature which you can find on the control panel for GoToWebinar. At the end of the presentation, I will unmute those who have raised their hands so that they can ask their questions using their audio. Once I unmute you, you might have to unmute yourself on the other end as well. If you have audio problems, I will ask you to type your question into the questions box, which can also be found on your control panel. Our first speaker today is Tim Lee from the University of Hawaii. Tim Lee obtained a PhD in 1993 from University of Hawaii and did postdoc research at GFDL and Princeton University from 1993 to 1995. He became an associate professor at the University of Hawaii in 1999 and a full professor in 2002. He obtained the University of Hawaii Board of Regent Medal for Excellence in Research in 2019. His Google Scholar citation number is over 14,000. Tim, thank you so much for joining us, and at this time, we will turn the controls over to you.
Thank you, Gabriel. Aloha, everyone. Actually, today's webinar actually consists of 2 talks. So first, I will talk about issues on MJO propagation dynamics, then followed by my PhD student, Yan Zhu, who just graduated recently. She will talk about two-way interactions between MJO and high-frequency waves over the Maritime Continent. First, I would like to acknowledge the support from NOAA CVP program managed by Dr. Sandy Lucas. So I want to start from this figure from Jiang et al. 2015, which show that the current state-of-art global models have difficulty in capturing MGO eastward propagation. So this observation, time, longitude, you can see the clearly eastward propagation of precipitation. And these 27 models, state-of-art model. Okay, so this observation in time, longitude section, you can see clearly eastward propagation from observation. Then they have 27 models here. So as you can see, only 1/4 of the models can actually reproduce those eastward propagation. This posed a great challenge for the model community. Various theories have been proposed in understanding MGO eastward propagation. Due to time limit, I'm not going to go through each theory. It seems that currently the most popular one is so-called moisture mode theory. The moisture mode theory can be separated further into the two types. One is PBR moisture asymmetry, another is column integrated MS tendency asymmetry. So this just diagram shows the first type of moisture mode theory, which emphasizes boundary layer moisture asymmetry. So what I show here is the vertical zonal cross-section of the anomalous equivalent potential temperature. Actually, moisture has a similar structure like this. So basically, as you can see, MGO convection is here, dashed line. So in the lower troposphere, moisture is in phase with convection, but in the boundary layer, moisture is leading, okay, leading the MGO convection. What is consequence of this moisture leading for the eastward propagation? So basically, the moistening in the boundary layer will cause the unstable stratification in front of convection, which causes the shallow convection, then gradually become deeper convection, which causes the convective system of MGO eventually moving eastward. The second type of the moisture mode theory emphasizes column integrated MS tendency asymmetry. So here is the definition for MSE, basically is CPT plus GZ plus LQ. Column MS budget, partial M, partial T is determined by 4 terms: vertical advection, horizontal advection, surface heat flux, and radiation. So if you look at the observation here, so you can see clearly this is time, again, time longitude section. You can see clearly eastward propagation of the rainfall anomaly associated with MGO. Rainfall is shading, and the counter is MSE anomaly. So as you can see, both MSE and rainfall, they move together eastward. So this is a horizontal view from observational point of view. You can see when the MGO convective center is at 80 degrees east in the Indian Ocean at day 0. And MSE anomaly is actually in phase with the convection. So there's no asymmetry, east-west asymmetry between MSE and convection. However, you do see clearly zonal asymmetry between MS east and west of MS tendency. So shading is MS tendency, the positive tendency to the east and the negative tendency to the west. It is because of this zonal asymmetry of MSE tendency eventually caused the eastward propagation. And also you can see that we have previous 27 models from Jiang et al. 2015, 7 best good model and 7 poor model. You see 7 good models show clearly eastward propagation, then poor model does not show propagation at all. Then look at tendency, you can see clearly this good model has very good resemblance in terms of MS tendency asymmetry, positive to the east and negative to the west, but there's no clear asymmetry for the poor model. So emphasis here is the second moisture mode theory emphasizes the MSE, vertical integrated MS tendency asymmetry. So now let me move to, I'm going to discuss 3 issues today. So first issue is talk about rule of the vertical MS advection in the eastward propagation. So this is the results of the moisture entropy budget from Jiang et al. 2017. So this is again using moisture entropy, but it's very close to MSE. As you see, the tendency of moisture entropy is mostly due to horizontal advection, but vertical advection is even negative. So there's no contribution to the eastward propagation. However, this is contradicted with our results. So my former postdoc Wang Lu and also Eric Maloney, Bin Wang, we have paper 2017 show that the vertical advection here is as important as horizontal advection. in contributing to the eastward propagation. So what is the difference between these two? So we found that the major difference is because the analysis domain. So in the pink domain, so this is MGO center, 80 degrees east Indian Ocean. The pink domain is from John et al. 2017, which is symmetrical by convection. You have 30 degrees to the west, 30 degrees to the east, so total 60 degree domain. And the black domain, the black box domain, is used by Wang et al. 2017. So this is a total anomalous MS tendency. You can, as I said, there's a positive tendency to the east and a negative tendency to the west. This is the MGO convective center here. The maximum center here, actually is beyond this pink region. So what I try to see is that if using this pink region to do the MS tendency analysis, you will neglect those maximum center. Here I show vertical MS advection and horizontal MS advection. Also, you can see maximum center, they all show beyond this pink region. So why are we using the larger domain? Because physically, we have some physical basis. So this is show dual model solution. If we have convection here, we know there's current wave respond to the east and the raspy wave respond to the west. And the horizontal length scale of current wave is much greater, 3 times as large as the raspy wave. Okay, so this is vertical view. You have ascending motion in the convective region, then you have descending motion. So this vertical overturning circulation, the horizontal scale, again, is 3 times as large as the raspy wave component. So as you can see from our MGO scale vertical velocity, ascending motion in the convective region of MGO, but descending motion here, maximum descending is away from pink region. Okay, so what is the consequence of those descending motion in the middle and upper troposphere in this infrared convection? As you can see, the mean MS looks like this. So you have maximum in the upper troposphere and the minimum in the middle troposphere, about 600 hectopascal. Then you have second maximum is in the surface. So this is the mean MS distribution. So you have vertical advection like this. You have positive tendency, positive vertical gradient, and also have positive vertical gradient in both upper level and low level. So which is important to cause the why you have center, vertical, maximum vertical to MS advection center is here, because this vertical velocity, okay? So that's why we believe the big domain has more physical meaning. So this is just our projection for each term project to the MS tendency. So this is from observation, this is from 7 good models group, this is 7 poor model group, and this is the difference between good and poor model. As you can see, the eastward propagation is most due to the vertical advection, the blue, and also pink is horizontal advection. This both plays important role. Then atmosphere heat flux and the radiation actually is negative rule. And you see good model basically match very well the observation one. But the poor model, horizontal advection still has some maybe 50% positive value here, but the most important problem in the model is vertical advection. As a result, good minus poor, the most serious bias is due to vertical advection. So this is in our paper, Wang et al. 2017, we proposed this new mechanism for the MGO propagation. So you have MGO deep convection here, you have stratiform cloud, ascending motion in the upper level, but descending motion in the front. In the low level, you have ascending because you have boundary convergence ahead convection. So you have first, second periclinical mode, vertical velocity. But the mean MS looks like this. So therefore, in the front convection, you have positive tendency. You have both vertical advection is positive advection in the front, but negative advection, to the west. So that's why you have east-west asymmetry. Those positive east-west tendency cause the eastward propagation. Okay. So now, let's move to the outcome planar simulation. So here, very quickly, because time limit, so outcome planar simulation have asymmetrical SST distribution, but you can, the model is generated MGO-like perturbation. You can see also clearly MS tendency, positive here, negative here. So there's tendency asymmetry. What causes tendency asymmetry? You can see vertical advection plays a very important role. Okay, vertical advection. Horizontal advection now is much smaller because in the outcome planet, the mean wind is easterly, which against eastward propagation. Okay. Second issue I want to talk about what is rule of the MGO raspy wave component on the eastward propagation. So there's controversy view on this. So where is drag effect, which is primarily based on wave dynamics. So you have stronger Rossby wave, then Rossby wave is moving westward, so therefore which has drag effect. But another one is acceleration effect. So this is based on molecular move theory of the second type, MS tendency asymmetry, because this is Rossby wave in the low level. So per equatorward flow will advect smaller MSE equatorward, so cause the stronger negative tendency to the west of convection, which enhanced zonal asymmetry of the moisture MS tendency. This therefore will accelerate MGO propagation. So we want to study from Rossby wave effect from aquam planar simulation. As you can see, we have three different SST profile: red, green, and blue. So red one here has slower eastward propagation of MGO. Here it has faster. So what caused this? You see the Rossby wave component. Rossby wave component intensity is represented by the shading, this vorticity, at 700 hectopascal. You see the Rossby wave is stronger in the faster propagation model or experiment. So therefore, a stronger Rossby wave component favors the faster eastward phase speed. Now, if you look at the 27 global model I just mentioned from Jiang et al., if you measure the MGO scale based on two, one is pattern correlation coefficient, another is phase speed. You see green, the slope is the phase speed. So each model has different phase speed. So you can see how they connect to the Rossby wave component for each model. So this is the results. So what do you see? No matter Rossby wave is defined by zonal wind at the equator, or meridional wind off equator, or by off equatorial vorticity, you have different definition. You always see the positive correlation between Rossby wave components intensity and the eastward phase speed. Okay, so our results show that a stronger Rossby wave component favors a fast eastward phase speed. So let's conclude the second issue here, the effect of Rossby wave on propagation. So both aquam planar simulation and diagnosis of 27 GCM simulation show that the Rossby wave has acceleration effect. So third issue is about, does the MGO move smoothly or jump? So as I mentioned, there's two types of moisture move theory. First type of moisture move theory, remember, we have convection here, but the boundary of moisture is leading. So this leading will cause the instability in front, then cause the shallow convection and gradual deep convection. So therefore, system is moving. But this kind of moving is jump from here to here. Okay. But another second type is talk about MSE tendency. So blue curve is MSE tendency, MSE itself, maximum is here, 0 degree. But the red curve is MS tendency. In the ideal case, I have 90 degree maximum MS tendency here, positive here, negative in the minus 90 degree phase. So, and then an analogy to the horizontal one-dimensional advection equation, partial u partial t plus c partial u partial x equal to 0. This is simple one. Mathematically, we do have a solution for that. This is smooth propagation at the speed of the c. Okay. So the second type implies that there's smooth movement for the MGO, but in the reality, what happens? So we can analyze this. A conventional way to estimate the propagation speed is based on slope, the green line. Okay, so this is lead lag regression coefficient. Time is here, longitude here, and the contour show the lead lag regression precision anomaly. Now you can see green curve is slope showing this is estimate, rough estimate of the phase speed. That's conventional way to do that. But as you can see, if you see the maximum phase actually has different phase speed. So now we develop a time normalization method. So basically at each time level, say each day, we try to search for the maximum convection location. As shown by black dots is maximum M prime, MSE anomaly, and the green dots show the maximum rainfall anomaly. Now both show very slow propagation here at 80 degree. Then you have suddenly jump from one longitude to another longitude. Okay, so therefore, if we look at the time normalization method, you see clearly the jump. So convection developed here and the decay here, and then suddenly jump to this place. So this is more detailed phase evolution with time interval, 3-day interval. for MGO scale different variables. Here is MSE, OLR, precision, Q2, Q1, and also vertical velocity. And this one is day 0, day 3, 6, 9, 12, each 3 days. You can see convection occur here, day 0, 3, 6. Day 9, now shifting to here, this location, then 12, 15, 18. So this MSE, OLR, precision, now all these variables show the similar jump feature. So you may wondering what determine the length and the time scale of this jump. So this is just show you pre-existing MGO convection is here. You see suppressed convection here. And this, according to your model, you have heating here, you have current wave response. So this figure shows geopotential high at 850 hectopascal and also zonal wind at 850 hectopascal. You can see maximum easterly is here. So this is a low level response to this heating to have easterly anomaly. So those low pressure and easterly will generate anomalous convergence in the boundary layer. Then, which will cause the moistening. Moistening will eventually cause the instability occurs. This theta E difference reflect convective instability. So emerging new convective center will be here. Okay, so you can see from one center to another center. So horizontal length scale is determined by the current wave response, the horizontal length scale of the current wave, of easterly wave in the lower troposphere. The time scale is determined by how the moistening process, the moisture accumulation, and also the development of this congested cloud to the deep convection. Okay, then I have to move to how sensitive the model to the other location. If 120 degree east, you see the similar features. So this is convection. If it's 120 degree, you can see the similar jump to the in front. So I just quickly let me summarize. A time normalization method was applied to illustrate the detailed evolution of maximum MGO convective phases. MGO maximum convective phases appears not to move smoothly, but jump. The jumping characteristics seems fitting better to the first type of moisture move theory, the boundary moisture asymmetry mechanism. I stop here. Thank you.
Thank you so much, Tim. At this time, if anyone has a question, please raise your hand and I will unmute you. I'm going to go ahead and unmute Dayan Kim.
Hi, Tim. Very nice talk. Really enjoyed it. I have a quick question about the issue 3. So have you considered that the MJO main convection center sometimes moves southward and move through the ocean between the Indonesia and Australia? So I wondered whether you consider that fact in this examination.
Yeah, that's a very good question. I think this right now for our analysis, we didn't consider that. We're just using like 10 degrees south to 10 degrees north or 15 degrees south to 15 degrees north average. We just only see the average feature here. And we didn't, but I believe one partial reason for stalling MGO convection stall here before the reach the maritime continent maybe is also related to this southward shifting of MGO convection. On the other hand, the reason I think there's fundamental reason for this jump, even without this shifting, I still believe there is jump. The reason is because, as I said, in a different longitude, even in 120 degree here, you still see this kind of jump. So this jump is still there. Maybe those southward shifting of convection before MGO reach the maritime continent may play some role for the when MGO convection is over the eastern equatorial Indian Ocean. But I think a basic feature of jump is still there. I guess that's my answer to simple answer to your question. Thank you.
Thank you very much, Tim.
I'm going to go ahead and unmute Bao Qing Zhang. I apologize if I mispronounce anybody's name.
Hi, Tim. Nice talk. So I have a following question about this third issue. So about circulation, it seems it does not have this jump. Is there any
Yes.
reason why the convection has such jump, but the circulation does not?
What do you mean? Okay. Okay. What do you mean circulation is not jumping? Actually, jumping
Like
every.
U850, it seems you have a longitudinal time diagram.
Yeah, this one. For instance, this is vertical velocity is also jumping.
How about zonal wind?
Zonal wind, I didn't show you here. You also see the jump because you see if convection is here, because gear responds to this vertical overturning circulation, and the current will respond, zonal wind. They also respond heating. If heating is here, wind should be there. Okay, so I think no, horizontal wind also have jump. Okay.
Okay. Thanks.
Great. It looks like that's all the questions we have. In that case, thank you so much, Tim. Up next is a presentation by Yan Chu from the University of Hawaii. Yan Chu graduated from the Department of Atmospheric Sciences at the University of Hawaii at Manoa and obtained her PhD degree in spring 2020. During her PhD period, she has been studying how the interaction between the MJO and HFW helps the eastward propagation of MJO. She hopes that her work can enrich the mechanism of the MJO eastward propagation. Yan, thank you so much for joining us, and at this time we will turn the controls over to you.
Okay. Hi everyone, it's my honor to be here to introduce my research work. Today I'm going to talk about interactions between the maiden-drilling oscillation and the high-frequency waves of the maritime continent. The maiden-drilling oscillation, or MJO, is the dominant mode of interseasonal variability in the tropics. It was first detected by maiden drilling in 1971, and after many years study, people found the MJO has some salient features, like it has interseasonal temperature scale, planetary pressure scale, and it slowly propagates eastward. And it has Kelvin-loss wave coupled horizontal structure and the westward tilting vertical structure. So why do I care about MJO? It's because the MJO has very important global impact. As an interseasonal variability, it can influence the active and break phase of the monsoon, impact the track frequency intensity of the tropical cyclone, and trigger the ENSO event, and as bridge to connect weather and climate systems, improving the understanding and simulation of the MJO. It's very important to the subseasonal to seasonal forecast. However, even though the tremendous effort has been put into the MJO study, many problems are still not solved. The eastward propagation of the MJO is one of them. In 2015, Zhang et al. Used 27 models to simulate the eastward propagation of MJO convection and found only 1/4 of them can capture this eastward propagation. And in addition, most MJO series about the eastward propagation only care about the MJO scale and not mention the effect of the high frequency wave. However, in 1988, Nakazawa has already mentioned that large scale MJO convection is comprised of many smaller scale convective systems. These convective systems may play a role of MJO eastward propagation, and in our study, we want to investigate the exact effect of this high frequency wave to the MJO. The work has two parts. The first part is about how does MJO modulate high frequency wave, and the second part is about how does high frequency wave feed back to the MJO. By studying these two-way interaction between the MJO and the high frequency wave, we want to enrich the MJO propagation theory. So here are the data and methods used in this study. We use the Lenker bandpass built to get different time scale components. The high frequency component is less than 20 days and represented by prime. Interseasonal component is 20 to 100 days, represented by the tilt line, and the low frequency background state component is longer than 100 days and represented by the bar. So here are the results of our study. We studied the MJO event with the convection located in the maritime continent, and the center of the convection is at 10 degrees south, 130 degrees east. And in MJO active phase in the low troposphere, we can see there is easy over and to the west of MJO convection and westly to the east of MJO convection. So how does this MJO modulate the high frequency wave? The figure here shows the difference of high-frequency wave vortices and deviation between the MGO active or sporadic phase and climate situation at 850 hectopascal. We can see the intensity of the high-frequency wave enhances over and to the west of the MGO compaction, and it weakens to the east of the MGO compaction. The intense change in the sporadic phase is opposite to the active phase. And from this horizontal structure, we can also see over the MGO compaction region, the high frequency wave is stronger in MGO active phase and is weaker in the sporadic phase. So why does the intensity of the high frequency wave change in different MGO phase? It relates to two MGO fields. In MGO active phase, there are easy vertical wind shear anomaly over and to the west of MGO compaction, and westerly vertical wind shear anomaly to the east of MGO compaction, and there is positive specific humidity anomaly. According to the one in 1996 and the 2006, it's found the easy vertical wind shear can cause the intensity enhance of some equatorial waves in the low troposphere, and with this positive specific humidity anomaly. The enhanced high-frequency wave can converge more moisture, so it causes more latent heat release and further increase the intensity of the high-frequency wave. So the intensity variation of the high-frequency wave are contribute to both MGO vertical wind shear and specific humidity. So in the above part, the high-frequency wave is the time scale shorter than 20 days. But actually, within this high-frequency wave, there are many compactly coupled equatorial waves, and their intensity variation to the MGO are different. Like this mixed Rossby gravity wave, its intensity is enhanced to the west of the MGO compaction and weakened to the east of the MGO compaction. The eastward and westward propagating initial gravity wave enhances over the MGO compaction, and the intensity of the compactly coupled K wave enhances over and to the west of the MGO compaction and weakens to the east of the MGO compaction. In order to test the relation between these equatorial waves and the MGO fields, we calculate the correlation between them, and here we see this mixed Rossby gravity wave. It shows significant negative correlation with the MGO vertical wind shear and no significant correlation with the specific humidity anomaly. This result is consistent with the result shown by one in 1996, and this indicates as the wave with shown rotational component and wave convergence component, the mixed Rossby gravity wave is sensitive to the change of background vertical wind shear, but not sensitive to the change of moisture. The burst initial gravity wave shows significant correlation with the specific humidity anomaly, but no significant correlation with this vertical wind shear because of their strong convergence component. And but this compactly coupled CAN wave, it shows because of its semi-quasi geostrophy and the gravity wave nature, so it shows significant correlation with burst MGO fields. So in the above part, what we talk about is all about the modulation from MGO to the high frequency wave. In the following analysis, I will introduce the upscale feedback from the high frequency wave to the MGO. There are two types of upscale feedback. The first one is from the nonlinearly rectified condensational heating. In 2012, she and Lee found their motion asymmetry is important to the eastward propagation of MGO. With the moisture in the east of MGO compaction in the boundary there, it triggers unstable and it causes the development of the shallow clouds. The shallow clouds gradually develop into congested clouds, and finally they become deep compactive clouds. So the eastward propagation of MGO is because of the decaying of old compaction and the developing of the new compaction in the east of the old compaction. And so this development of the shallow clouds is the precondition of the MGO compaction eastward propagation. And we found the nonlinear rectification of a high frequency wave contribute to this development of shallow clouds. Here is the equation of Lagrange motion sink. This interseasonal filtered Q2 dominated by the MGO compression is shown in the first column in the figure. We can see this condensational heating of the MGO gradually propagates eastward, and in the east of the MGO compression, there is condensational heating of shallow and congested clouds. By averaging this condensational heating in the east of the MGO compression, we can see this gradually intensified and upward developing condensational heating more clearly. So, how does the high frequency wave feedback to this developing process? There are two types of atmosphere feedback from the high frequency wave. The first one is called Q2LH. The Q2LH is the condensational heating contributed by the nonlinear rectification of high frequency wave with low frequency background state components. And another one is called Q2TLI. The Q2TI is the condensational heating contributed by the nonlinear rectification of high frequency wave with space interseasonal and the low frequency background state components. Both Q2LH and Q2TI don't have the interaction between interseasonal and the low frequency background state components. And from figures, we can see both interseasonal Q2LH and Q2TI show positive anomalies in the east of the MGO compression, and these positive anomalies propagate eastward along with the MGO compression. So, which indicates these Q2LH and Q2TI can be important contributors to the this condensational heating of shallow and congested clouds. And we calculate this contribution fund is about 25 to 40% if taken 1,000 to 700 hectopascal is bounded there, and it can be 40 to 60% if taken 1,000 to 850 hectopascal is bounded there. So from right now, we already know the Q2LH and the Q2TI are essential to the establishment of the shallow and congested cloud, but there are many terms within the. So in order to find the mechanism, we need to find the dominant contributor. By separating every term, we find the largest contribution is from this interseasonal eddy meridional motion advection. This term shows apparently a symmetric feature with positive anomaly in the east of MGO compression and negative anomaly in the west of MGO compression. And in order to explain this interseasonal eddy meridional motion advection, we plot the wind and the specific humidity of high frequency wave at 850 hectopascal. We can see there is positive anomaly of this specific humidity and a positive specific humidity anomaly in the south of this northwesterly and negative anomaly in the south of this southeasterly. So this advection of the meridional wind to the motor is negative advection. And as we mentioned in the modulation from the MGO to the high frequency wave, the intensity of the high frequency wave weakens to the east of the MGO compression. So this negative advection will also be weaker, and it shows positive anomaly when projected to the interseasonal timescale. And we also give the physical explanation of this mechanism with this schematic figure. In the MGO active phase, the intensity of the high frequency wave weakens to the east of the MGO compaction, and so its ability of mixing dry air from extratropics to the tropics is weaker, and more moisture remain in the tropical region for the development of this shallow and congested clouds. And this shallow and congested clouds have the eastward propagation of MGO compaction. So the second type of atmosphere feedback is from the eddy momentum transport. The figure shows the MGO sonar wind and the sonar wind tendency. We can see in the low troposphere, there is easily over and to the west of MGO compression and westerly anomaly to the east of MGO. There is westerly over and to the west of MGO compression and easterly to the east of MGO compression, and the positive sonar wind tendency over the MGO sonar wind transitional region which indicate the eastward propagation of this MJO sonar wind in the next moment. And because of the baroclinic structure, so this MJO sonar wind and sonar wind tendency in the high level are opposite to the low level. So this sonar wind tendency anomaly in the MJO sonar wind transitional region is the key to the eastward propagation of the MJO sonar wind. And we want to find how much is the nonlinear rectification of the high frequency wave contribute to it, and what's the mechanism behind this contribution. Here we use the momentum budget analysis. The MJO sonar wind tendency is divided into different timescale interaction terms. All terms with high frequency component are included in the term A, and the terms without high frequency component are included in the term B, and the term total equals to term A plus term B. Here we calculate the contribution from the intersystem term A to the MJO sonar wind tendency in the least sonar wind transitional region in each level, and we found the largest contribution is at 850 hectopascal, about 60%. So in the following analysis, we will focus on this level. The figure here shows the MJO sonar wind and the intersystem term A and the intersystem term B. We can see this center of this intersystem term B is in phase with the center of the MJO sonar wind. So it mainly has the amplitude growth of this sonar wind, and the center of the intersystem term A is in phase with this MJO sonar wind tendency. So it mainly has the eastward propagation of the MJO sonar wind. However, still there are many terms within this term A. So in order to explain the mechanism of it helps the MJO sonar wind propagation, we still separate off them and find the largest contributor is this intersystem sonar eddy momentum flux divergence. So how does this term contribute to the MJO sonar wind tendency? As we mentioned in the modulation from the MJO to the high frequency wave, the intensity of the high frequency wave enhances over and to the west of the MJO convection and weakens to the east of the MJO convection. So it will cause this positive intersystem sonar eddy momentum flux over and to the west of the MJO convection, and the negative anomaly of this term to the east of the MJO convection. So the divergence of this intersystem sonar eddy momentum flux shows positive anomaly over the MJO sonar wind transitional region, and this positive anomaly contribute to this positive MJO sonar wind tendency and helps the eastward propagation of the MJO sonar wind. So the two types of upscale feedback we talk here all start with the modulation from the MJO to the high frequency wave, then the modulated high frequency wave feedback to the MJO. This is what we taught the two-way interaction between the MJO and the high frequency wave. Here are some conclusions of this study, and that's all. Thank you for your listening. Do you have any questions?
Thank you so much, Jan. Again, if anyone has any questions, please raise your hand and I'll unmute you. Also, feel free to use the questions box. I'm going to go ahead and unmute Diane Kim.
So you showed that the high frequency eddy moisture fluxes, flux convergence plays some role in the maritime continent. I wonder whether you have a sense of the geographical distribution of those effects. I mean, we also know that the high frequency eddies are playing some significant role over the Indian Ocean and also in the Western Pacific. And you specifically looked at the effect of high frequency eddies in the maritime continent to have a sense of whether the effect of high frequency eddies is comparable between ocean basins and in the maritime continent, and or do you see a bigger or smaller role in the maritime continent? Is my question clear to you?
Yeah. Okay. So at first we study this modulation, the interaction between the MGO and the high frequency wave is because in the maritime continent, the intensity of the high frequency, the intensity of the MGO weakens, and also some MGO events stop there. So we want to figure out maybe where a high frequency wave contribute to it. So and actually we found in our study the high frequency wave actually contribute to this MGO propagation. And in the data, we also do some study, you mentioned in Indian Ocean, West Pacific. Actually, the conclusions in Indian Ocean is actually similar to the maritime continent, and there's some difference in the Western Pacific region because the MGO events after it's propagated, because we study the high frequency wave in the east of the MGO convection. So when it's propagated to the Western Pacific, in high frequency wave in east is already maybe reached a little bit close to the Central Pacific. So it's a little bit different, but the conclusions in the Indian Ocean is very similar.
Thank you.
It looks like Tim Lee has a comment. Tim, go ahead.
Okay, I think Professor Kim asked a very good question. What is the major difference between the MGO modulation over maritime continent versus Indian Ocean and the Western Pacific? I think you have to first talk about MGO intensity. So MGO intensity in the Indian Ocean actually starting from weak and then gradually growing, because all the response, like vertical shear, like moisture, all those is associated with intensity. So over the maritime continent, when the MGO is reached 80 degree, 90 degree, you have maximum intensity of MGO. So therefore, you would expect a stronger circulation response associated with this heating. On the other hand, if you look at the background mean state, over the maritime continent region, particularly South Equator, is a monsoon, Australian monsoon region. So you have background state is also very strong. So MGO is strong during before the reach the maritime continent, and also background state is also variable for the development of the MGO as well as the high frequency waves. So I would see the high frequency wave development is much stronger over the maritime continent region where monsoon reside. Western Pacific actually, you will see the shifting because SPCZ. So when MGO moved to the maritime continent, the high frequency variability in front of MGO actually were shifting southward because SPCZ. So I think environmental conditions should be considered also. But in general speaking, you do see this pattern. So enhance the variability, high frequency variability to the east, over the MGO center and also to the west of the convective center, but suppressed high frequency variability to the east of this MGO center. This one satisfies for all the region, maritime continent, Indian Ocean, and Western Pacific. But the intensity of those perturbation might be depend on mean state and also MGO intensity. So that's my comment.
Thank you, Tim, for that comment, and thank you, Jan, for your presentation. We would like to thank you all for joining us for this set of presentations in our series on Years of Maritime Continent. I would like to thank today's presenters for taking the time to share their work with us. The recording of today's webinar will be available within the next week on our website, cpo.noaa.gov/CVP. We hope you will join us for the next webinar on October 8th. Thank you so much.